There is a number so large that writing it out in full would require more digits than there are atoms in the observable universe. And for most of human history, we assumed the universe itself was smaller than that number. We were wrong, by a margin that doesn't have a name yet. For centuries, scale was something we thought we could eventually grasp. The solar system felt enormous until we measured it. The Milky Way felt infinite until we mapped its edges. The observable universe felt like everything until we started asking what observable actually means, and realized it is not a description of the universe's size. It is a description of our limitation. What lies beyond that horizon isn't empty. It's just permanently, physically unreachable by any signal, any probe, any thought experiment we could ever construct. And the James Webb Space Telescope, by looking deeper into the universe than any instrument before it, didn't just extend our view. It revealed how profoundly we had been underestimating what we were looking at all along. Start with the simplest fact. The universe you can see, the sphere of space from which light has had enough time to reach you since the Big Bang, spans roughly 93 billion light-years in diameter. Not 13.8 billion, the age of the universe in years, 93 billion. The difference exists because space itself has been expanding the entire time that light was traveling toward us, stretching the distance between its source and our eyes even as the photons crossed it. The light that formed our cosmic horizon left its origin point when the universe was almost unimaginably compact. By the time it reached us, the object that emitted it sits tens of billions of light-years farther away than it was when that light first departed. We are not seeing where things are. We are seeing where things were, from a distance that has continued growing every second since. That distinction matters more than it might first appear. Webb was built to push that look-back window as far as physics would allow. Its gold-coated mirror, spanning 6.5 meters across, collects light in the infrared spectrum, wavelength stretched beyond what human vision registers, stretched precisely because the universe has been expanding since that light was emitted. The farther the source, the more the light shifts. The more it shifts, the colder and longer the wavelength becomes. Webb's instruments were cooled to roughly 233 degrees below 0 Celsius, specifically so the telescope's own heat wouldn't drown out signals arriving from the edge of the observable universe. Every design choice, the mirror size, the orbital position nearly 1 million miles from Earth, the 5-layer sunshield the size of a tennis court, was engineered around a single goal: see the farthest things. And when it did, what came back wasn't just more data. It was a confrontation with what more actually means at these distances. The galaxy catalogued as JDSGSZ 14-0 sits at a confirmed distance corresponding to just 290 million years after the Big Bang. That sounds abstract until you translate it into light travel time. The photons Webb captured from that object had been traveling for approximately 13.5 billion years before they landed on its detectors. Every second of that journey, the universe was expanding around them. The galaxy they came from isn't where it was when they left. It isn't where it appears to be now. And the light Webb has not yet received from objects beyond that horizon is still traveling, from sources that emitted it even earlier, from regions of space that have been racing away from us since the very first fractions of a second after the cosmos began. Here is the part that changes something fundamental. The observable universe is not the universe. This isn't a philosophical point. It's a geometric consequence of physics. The speed of light is finite. The universe is old enough that regions sufficiently far from us have been carried beyond the distance light could ever bridge, not because they're moving faster than light in any conventional sense, but because the space between us and them has expanded faster than light could cross it. There is a boundary, the cosmic event horizon, beyond which anything that exists right now is permanently beyond our reach. Not unreachable by current technology, unreachable by any technology ever under the physics we know, and the universe beyond that boundary is not small. Conservative estimates suggest the full universe, if it is finite, may be at least 250 times larger than the observable portion. Some models place it far larger still. Others entertain the possibility that it simply doesn't end, that what we call the universe is a local bubble inside something without boundary or edge. Webb's newest deep field images make this visceral in a way that no previous instrument could. A single image covering a patch of sky equivalent to a grain of sand held at arm's length contains thousands of galaxies, each one an island of hundreds of billions of stars, each one separated from its neighbors by millions of light-years of mostly empty space. And that image represents an almost inconceivably tiny fraction of the total sky. Scaled up to the full celestial sphere, estimates place the number of observable galaxies in the range of 2 trillion. 2 trillion separate gravitational systems, each containing stars by the hundreds of billions, each star potentially hosting worlds, and all of it compressed into the fraction of the universe that happens to fall within the range of instruments we have built so far. The scale doesn't stop being strange when you absorb the numbers. It becomes stranger. Consider what emptiness means at these distances. Between galaxies, space is not merely empty in the way a room is empty when nothing occupies it. Intergalactic voids, the vast underdense regions between the filaments of the cosmic web, span hundreds of millions of light-years. If you could somehow travel through one at the speed of light, you would spend hundreds of millions of years seeing almost nothing. No stars, no gas clouds dense enough to collapse, no light from any source close enough to be visible. Just the faint cosmic microwave background glow, the afterglow of the Big Bang itself, surrounding you equally in every direction. And those voids are not exceptional geography. They make up most of the universe's volume. The glittering structure we photograph, the filaments and clusters and superclusters, represents a thin foam of matter clinging to the surface of mostly nothing. Webb made this architecture visible in unprecedented detail by tracing the large-scale structure of the cosmos back into epochs when its patterns were still forming. Galaxy clusters, already clearly linked by filaments of dark matter scaffolding, appeared far earlier in cosmic history than models predicted they should. The universe's architecture wasn't assembled slowly in the way its equations suggested it would be. It built itself faster, denser, and at larger scales than anything running on a conventional simulation had reproduced. The scaffolding was already going up when the universe was a fraction of its current age. And the structures found in that scaffolding aren't small by any measure we brought to the question. One confirmed superstructure, the Hercules Corona Borealis Great Wall, spans an estimated 10 billion light-years in its longest dimension. That single object is roughly 10% the diameter of the entire observable universe. Its existence challenges the cosmological principle, the foundational assumption that the universe, viewed at large enough scales, looks roughly the same in every direction and from every position. If structures this large can form and persist, then uniformity on the scales where our models require it may not hold. The maps we built from the assumption of smoothness may be drawing the wrong universe. And what Webb keeps finding in those maps is that the universe did not wait for permission to build big things. This is where size and time become impossible to fully separate. The objects Webb has confirmed at the farthest distances aren't small, primitive, fragmentary early attempts at structure. Some are massive. Some contain more stellar material than anything nearby had any right to achieve that quickly. The galaxy at 290 million years after the Big Bang stretched over 1,600 light-years across and already contained hundreds of millions of stars. The models that existed before Webb predicted the universe would need far longer to accumulate that kind of mass. Those models described a patient cosmos, slow accumulation, gradual collapse, structure earned over time through a long and careful gravitational negotiation. What Webb photographed was none of that. It was scale arriving ahead of schedule, by margins that have no easy explanation in the standard framework. The unsettling implication isn't just that the early universe was more efficient than expected. It's that efficiency at that scale changes what we think the word early means. If galaxies were already large, already chemically enriched, already hosting generations of stars that had lived and died within the first few 100 million years, then the universe was not in its infancy at that point in the way the timeline assumed. Something like maturity was already underway. And if that's true, then the universe's full story is longer and more complex than its measured age alone would suggest. Its beginning was more violent, more productive, and less gradual than the smooth transition out of the Big Bang we modeled from the calm present. There is a version of this realization that is almost impossible to sit with comfortably. The observable universe, all 93 billion light-years of it, all 2 trillion galaxies, all the filaments and voids and superclusters, all the early galaxies Webb has found that shouldn't yet exist, all of that may represent less than 1% of what actually exists. The universe doesn't know we're here. It didn't consult our models before deciding how large to become. It has no edge visible to us, no center we can locate, and no particular concern for the frameworks we built to contain it. Every time an instrument has pushed the boundary of what we can see, the universe has responded not by showing us a wall, but by showing us more of the same, stretching further in every direction, further back in time, further beyond what the previous generation of instruments could reach. Webb is not the end of that process. It is a step in it, and every step has returned the same message: there is always more. That message carries a particular weight when you consider what it means for what we cannot see. The 2 trillion galaxies in the observable universe are the ones whose light has had time to reach us. Beyond the horizon, the same physics that produced those 2 trillion galaxies presumably continued operating. The same processes of dark matter collapse, gas cooling, star formation, and gravitational assembly ran in regions we will never observe, producing structure we will never detect on scales we have no way to measure. The universe that exists beyond our horizon is not hypothetical in the way that untested theories are hypothetical. It follows from confirmed physics. It's real. It's just permanently invisible. And it is almost certainly vast in a way that makes the observable universe look local. That's not a metaphor. It is a measurement's honest consequence. And here's what that leaves behind when the numbers finally settle into something closer to feeling than arithmetic. Every civilization that has ever asked where it stands in the cosmos has had to revise its answer towards something smaller and more peripheral than it previously imagined. Earth wasn't the center. The sun wasn't exceptional. The Milky Way turned out to be one of 2 trillion. And now the observable universe itself, the outermost boundary we have ever been able to probe, reveals itself as a window, not a wall. What Webb found wasn't simply more galaxies. It found evidence that the universe had been larger, faster, more productive, and more structurally elaborate than we had built into our deepest equations. It found that the scale we thought we were measuring was a fraction of the scale that actually exists. You are not standing at the edge of something. You are standing somewhere in the middle of something that doesn't have a discoverable edge. Every direction you look, even with the most powerful telescope humanity has ever constructed, terminates not in emptiness, but in more. More galaxies, more history, more structure assembled by physics that didn't need us to understand it before it began. The universe has been working on this for nearly 14 billion years. Webb gave us a slightly better window onto that work. And even through that window, what came back was enough to make every previous estimate of this place feel quietly like an apology for how badly we had underestimated it. The real question Webb left open isn't how large the universe is. It's whether we are capable of genuinely imagining an answer, and what it means for everything we thought we knew that, so far, we are not.